Okay. So you read about it in your book, and now it's time. It's time to go through this in class. Computational complexity. Let's do this. So before we get started there, let's just talk about all the stuff that we've learned so far with C++, because now we've graduated away from object-oriented programming lectures, and now we are going to talk about data structures and algorithms. Okay, so we talked about constructors. Those are for initializing yourself, so giving yourself a nice starting value. If you're a counter, if you're a stopwatch, whatever you want to be, you need an initial value, or multiple initial values. If you're a vector, for example. And then copy constructors, we learned about those, and those are for cloning somebody. So if I already have like a counter, and I like the value that one's sitting at, maybe I like the value 1 or something, I can say counter D and get a clone of C placed into D. Okay? And then copy assignment operators are essentially the same thing. You're also cloning somebody else, but you have to get rid of your own stuff first, usually if you've allocated things. So maybe you made a counter E, and then you want to do something like E equals D. And depending on whether or not your counters use heap values, you might have to start deleting things out of E to not leak memory, okay? And you don't want to do the default thing either by copying over pointer values, which are just addresses. And that is also a bad thing. We noticed that we had a bunch of objects pointing to the same place on the heap, and that causes weird things to happen. Okay, so that's copy assignment, and sorry for the colorful sentence there. I've been reading the Iliad. All right, so destructors are essentially the opposite of constructors. They're for cleaning up after yourself. After you're all finished, I have some stuff probably on the heap, and I need to go, here's my object, and it's pointing in many places to the heap. I just need to go and get rid of those things, or something else, like I need to close a file. Whatever you need to do to get rid of stuff is the job of a destructor. Okay, just normal cleanup operations. And so far we've talked about deleting stuff off the heap. Okay, so destructors for cleaning up after yourself. And that's our recap. We're ready to move on. So here's my goals for you, and let us get motivated, because I love this topic. So let's pretend we are a rabbit farmer for one reason or another, and we want to buy efficient rabbits because maybe we sell them, or like we harvest their meat or something. I don't know. But we have the option. We got some rabbit A's, and they reproduce according to this formula. 2000n, where n is days. So on day 0, I have 0 rabbits because I haven't bought any yet. But on day 1, I suddenly have 2,000 rabbits. That sounds like a sweet deal, right? And then on day 2, these rabbits don't waste any time. On day 2, I have 4,000 rabbits, and we're going like that. We're moving on up in the world. Okay, so that's my formula. Or you have the option of buying 2 rabbit bees who reproduce according to the following formula, 2n squared. Now, which rabbits do you buy? Okay, that is the question, and you've already read this stuff in the book, but I just want to make it more colorful and exciting and like grill it into your minds. Okay, so 0. So on day 1, on day 0 I still have no rabbits, as usual. On day 1, I have 2n squared, so n squared is still 1, so I have 2 rabbits. And then on day 2, I have 2 squared is 4, times 2 is 8. 2, 4, 6, 8. I have 8 rabbits. And this is going to look like a parabola, eventually. And these are some pretty small numbers. Surely, I should go for rabbit A, right? And you know where I'm going with this, but let's pretend you didn't, and let's write a program. The simplest program we're going to write in CSCI 41. Okay. This is lecture 7. Welcome to lecture 7. So, alright, got nothing there. Let's make rabbits.cpp. Alright, so here is our first option. So if I go with rabbit A, they're going to reproduce according to this formula. So let's go with int rabbit A, int, I guess, day represented by n. So on day n, I have 2,000 times n rabbits. Okay, and then rabbit B is 2n squared rabbits. All right, so let's watch these converge. So while true, so int day starts at 0. So cout day 0, new line, and then we'll tab over and be like rabbit A's that we currently have if we were to have bought rabbit A's. And same thing for rabbit B's. Alright, yeah, that seems about right. And then, obviously, we're in a while loop, we should probably increment day. Let's do this. Make that a bit bigger. Over there with you, or maybe down here. Okay, kind of do it the old school way. Let's not make a makefile just yet. No real need, and that's wrong. So I have done a few things that are not correct. Day, and then a colon, and then a new line. I was getting too excited about day 0, apparently. What else? That's probably correct. Oh, and I think I want to stop it. Like, I want us to keep on, like, I want it to wait and ask, and we'll see if we want to continue this loop. Okay, so I'll have it just, like, get some input. Alright, let's try this. Day 0. 0 rabbits of either kind. Now I'll hit enter. Day 1. Yeah, this is much better. So, A's are beating B's. A's are doing quite well. Oh yeah, look at the rabbit A's. These rabbit B's are puny. Those are worthless, right? Right? Dun dun dun. And we're off to the races. So, let's see how we do. Dun dun dun. Slowly but surely. The rabbit B's, I guess this all depends on when you want to sell these rabbits, but slowly but surely, the rabbit B's are going to catch up. And I don't know how long we want to wait for this, but I think we're getting there. Are you ready? Are you ready? Oh, okay, let's see. Let's see here. Oh man. Okay. By at least day 1009, we have finally surpassed rabbit A's. So this is a long-term investment for rabbit B's apparently, but you will come out ahead in the end if you go with the n squared over the linear. Okay, so these rabbits reproduce linearly, and these rabbits reproduce, what's the word? Quadratically, or like polynomially, or whatever you want to say. This is quadratic. It's an n squared. Dun dun dun. And yeah, so you're gonna want to buy rabbit B's. And that is the story. So eventually, there's going to be some time in the future, day 1009, where the rabid bees will start winning. And that's all we need to know. So that brings us to complexity. And there's a fun little quote that I like. Feel free to pause and read that. But complexity is all about figuring out how fast a program thing, and we're calling it computational complexity. And my computer froze for a second. I hope you can still hear me. And everything's fine. So, yeah, computational complexity is the amount of resources that a program is needing. There are more than these. There's more than just time and space, but these are the ones we're going to focus on in this class. And, well, how do we measure these things? I know you've read about this, but pretend you didn't. And, well, maybe your question's like, all right, I have a microwave that has a processor inside of it, but it's a lot slower than my computer. How in the world am I going to time my algorithms? How does that even make sense? How can I give a universal amount of time? And we use math to do that. We use equations. Beautiful, beautiful equations to measure how complex a program is. We don't use absolute time, usually, when we're talking theoretically. But we can use that to get started, and I'll have you time some stuff in your lab this week. So, here's a loop. Another simple program. How in the world does it execute? And you can ask a question about how many times it does something. So how many times does this loop execute its body? Okay, so maybe pause. This is a good example question for the midterm, maybe. Well, I goes from 1 to n. I sure hope that you said n. It's going to execute its body n times. Well, what does that mean in terms of time? And it's actually quite nice. It does correspond to some amount of time, because our processors, they work at a certain clock speed, and they have a clock cycle that goes ever so fast, and it's always the same speed. And that's a beautiful thing, because we can use that to measure. So a 2 gigahertz processor, for example, can tick, like do this little thing, have a clock cycle 2 billion times a second. So that's a lot of computation, because you can do an individual computation each clock cycle. All right? So here are some things that take 1 clock cycle, or I want you to imagine that they do. Okay? You can have an assignment statement, semicolons all around. Pretend, or assume that that is going to take 1 clock cycle. That is usually the case. Okay? And then array or vector access. If you want to index into something, x is really close. It's a memory address. We just need to offset that by a little bit. That, let's assume, takes 1 step of time. Okay? Again, once you get into CSCI 45, this is going to not be the case, but it's all going to... It's not a huge deal that I'm lying to you right now. Okay? I promise that. Basic math, that is for sure going to take it, assuming it's on ints at least. That's definitely going to take a clock cycle. That is always the case. Same for comparisons on primitive values. Outputting, you can also assume, takes a clock cycle, takes 1 step of time. And that's probably the biggest lie. But that is the idea. So essentially, if you have 1 line of code and it's super simple and it doesn't call any functions, you can assume that that takes 1 step of time. Okay? So that's how I want you to think about your programs for the rest of time. All right, so with that, let's figure out how many steps we need to take to execute the following code. So maybe pause this video, circle things, and we'll come back together. All right. So let's count all those operations from back here. Let me make sure this is still recording, just in case something went horribly wrong. All right, so we have pluses, we have minuses, we have assignments, we have a comparison, another assignment, a plus, and then an output of, I don't know, either 1 or 2 things, depending on how you count. So maybe we'll just be like 1, 2, so I'll count all the circles, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is about 9 steps. And we can count this, which means it's constant. We've talked about that word before, but we'll talk about that some more later, don't worry. Okay, now back to the loop. Now that we know how to do this, how many steps does this one take? So, this is going to happen. This is a plus and an assignment. Dun dun dun. That's going to happen once. That's a thing that happens every iteration of the loop body. This also happens after every iteration of the loop body. So now this kind of depends on n. Do you see that? So we have to use n somewhere in our equation. We can't just say, oh, yeah, it's 9 steps every time. No, it depends on whatever n was, how many times this loop executes. Here are the things that are all going to happen just once, I think. So this line is going to happen just once, this line is going to happen just once. So those are out of the way. So that's like, we have at least 2 already. Okay, that's 2 steps, and then this stuff gets repeated, but how many times? So this body executes n times, okay, but how many things does it do inside of its body? It does this, the assignment, the increment, and then also the comparison. So it's in order. It's going to be compare, see if it's true. If so, execute the body, which involves a plus, an assignment, and then an increment. So that's 4 things every loop iteration. So 4 steps each iteration. So that'll iterate n times. I'll do that. So that's 4 times n. And then at the very last iteration, it'll be like I++, and I is now n plus 1. And so it'll have to do this this comparison one last time so that it knows that it's done with the loop and we can move on. Okay, so this gets happens 1 extra time. So it's not 2 plus 4n, but 1 more. So it's 4n plus 3 steps. Okay? Now, you never have to count this as long as you remember the rest of this lecture, but it's a good exercise, I think, to get a good number, to see what this means. Like, okay, if my processor can do, I don't know, 2 billion cycles a second, how many times can I execute this loop, depending on the value of n? Okay, in a second, perhaps. Now, what we're looking for, like our end goal, is a way to compare algorithms, because we want to be like, yeah, my algorithm is awesome, yours sucks. And so we want to make it so that it's easy to talk about the relative merit of 2 separate algorithms. And it just so happens that we start dropping things from our equations because of that. And I'll show you why on this slide and after this slide. So 4n plus 3 was our original count for this loop over here. But, well, this is just a very precise number. Like if I added 1 extra line, like, I don't know, cout sum, now suddenly it's 5n plus 3. Was that a big deal? That's the question. And that's honestly not going to be a big deal for us. And also the plus 3, let's talk about that first. The plus 3 is not really going to do much for us. If we zoom in, like here's legit x equals 1, x equals 2, x equals 3. Sure, 4n plus 3 and 4n look quite different from one another. They're so spaced out, right? But the second we start zooming out, they are identical. So as n gets large, I should write that, as n gets large, because that's what we want to do when we compare algorithms. We want to compare against large n values. We want to deal with billions of ints at once. As n gets large, that plus 3 doesn't matter much. Okay, so that's honestly half the idea. So the rule, our first rule, when we are talking about algorithms and giving them an equation to represent how fast they are in terms of time, we're going to drop the lower order terms. So 4n dominates the plus 3, which is a constant, as n gets large. Okay, because you can start zooming out, and then the plus 3 really goes away. Okay, even if it was plus 1,000,000. You could zoom out, and I guarantee you that you'd find this picture again. You might just have to zoom out farther. Okay? That's the idea. So drop your lower order terms from your equation. And then also, we're going to drop the constant factors as well, because it really isn't a big deal to add like a, I don't know, add a cout statement here. I'll put this in green so that when you come back later and you're like, why is he doing this? You will remember that it was an addition. Cout sum. So if you were to do that, then it would suddenly become 5n plus 3. Well, it's just one extra thing. Like, that's not a huge issue, right? And that is the right assumption. That is the right intuition. So, where were we? We were here. 4n and n, sure, when we graph them right next to each other, that's this one and this one, when we graph them by themselves, they sure look the same. Or they sure look very different. Like, this one's going off that way, this one's going off that way. Of course, they're not curved, but you get the idea. But the idea is, it's just one extra line per loop. It's not a huge issue. And because we're in the market to compare things, we want to compare when things are super different. So when there is a higher order term somewhere, that shows us that our quibbles about the constants mean absolutely nothing. So we want to be able to compare 4n not with n, but with n squared. Like, this is an arguably much worse version of this algorithm. Okay, so we care about the terms, the highest order terms. All right, so we'll also drop these constant factors. We'll just say that 4n is essentially n to us. So our final, what we've done is we made this jump, 4n plus 3. That's essentially 4n, and now I'm saying that 4n is essentially n, because once we start comparing against other terms with different orders, like not just a line anymore, but like a parabola, you start zooming out there, that those constants in front mean absolutely nothing. Okay, so here's just close up, zooming out, and then zooming out a whole lot. 4n and n really meant nothing. Okay, so let's just call it n. Drop those constant factors. All right. And so that brings us to this idea called big O notation. That's what we use pretty much all the time. If you ever get into an interview about programming, you'll be asked to say how fast your algorithm that you just implemented on the whiteboard takes. What's its time complexity in terms of big O notation. And so that's what this is. Okay? So we've discovered how to do it. So we make a few simplifications. So we count steps instead of absolute time. So we're not putting a stopwatch next to our computer's clock. We're counting steps depending on input, okay? Depends on input. So we give our input a variable value. Usually we use n, okay? So there's always going to be a variable somewhere unless it's a constant, okay? And then we ignore lower order terms. So say we had 4n plus 3, we can drop the 3. Say we had n squared plus 2n, we can drop the 2n. Because, again, with this whole zooming out idea, the dominant term in the end, once you zoom out far enough, this one's always going to win. It's always going to look mostly like n squared, okay? This might mess with the graph a little bit as n is small, but eventually it's just going to look exactly like n squared if you zoom out enough, okay? That is the idea. Now, yeah, so we're going to ignore those lower order terms, get rid of those constants. And finally, we'll ignore any constants that are coefficients in our leading term. So we'll talk about n log n eventually in this class. You can't drop either of these because they both depend on n. Neither of these is a constant, okay? But you can drop the 4 in the 4n plus 3, because that's just a constant, okay? So this is just n. Or, hey, I've already got it in a box. There we go. Drop the 4 as well. Okay, so what we've noticed about our initial loop was that the running time grows linearly in n. That's what we say. So the runtime given these steps and given just n by itself, it's growing essentially in a straight line. Okay? Well, it's growing exactly in a straight line. It's just offset a little bit. So we say that the runtime then is O of n. We put the simplified thing inside of an O in parentheses. Okay? That is all you have to do. You have to write an O, write parentheses, and then write your simplified equation in the middle. That's all you have to do. And this is called big O of n. And this is big O notation. Okay? Not too bad, I hope. Please yell at me about this in office hours if it's not making sense. This is a bit more math than we're used to, and this is going to keep happening in this class. So just in case you're like rusty on your math, we're going to get you there. All right? So now let's move on to best case and worst case. So our algorithms, they don't always take the same amount of time, right? So maybe I can start typing this. We just noticed that they can depend on n, for example, like the size of our input. Maybe I can write that as well. We know now, at least, that they can depend on the size of input, for example, but that's not the only thing. They can run differently depending on the input as well, okay? Some algorithms might run significantly faster for some inputs. And so that's the idea of best case and worst case. So the best case is as fast as possible, like the clouds parted, the stars aligned. This is the fastest your program could ever possibly run. All right, so like stars aligned, clouds parted. The fastest your program can run. Like if you got to choose the input that would make your program as fast as possible, you're going to pick this one, right? You're going to pick the best case. Okay? And then worst case is, of course, the opposite. That's when your worst enemy picks the input to the program. Eee. And it runs as slow as humanly possible. Okay, so that's what we call the worst case. And that depends on the input. Okay? Best case, worst case, kind of self-explanatory, but think about it as in the best case, you get to choose. You can pick the thing that makes your program run as fast as possible, like you choose. And in the worst case, your worst enemy chooses. It's like Pokemon, okay? Now, let's give an example of that now. So maybe pause the video, try and understand what this program's doing, and I don't know why it's so not spaced out. Let's fix that a little bit. That's better, but that's off the screen now. Let's make it 0.8. That is slightly better. Okay, so we're going to get input from user twice, apparently. Option and n. And look at what happens if option is 0. And look at what happens if option is 1. Oh man. So, just quickly, if the option is 0, how many times does this body execute? Dun dun dun. N times. So, I guess it's lowercase n in this example. So this is an O of n algorithm if it's option 1, or option 0. Because this is just, it's all dependent on this n. This body's going to get executed n times, and this is constant work inside of here. Okay, so now we can finally go back to this slide. Anything that runs in constant time with a constant number of steps is O of 1. All right, so all this stuff, everything here. This is O of 1, this is O of 1, etc. Okay? All of this stuff. We're calling it O of 1. So if we're doing, I'm saying that this is O of n, and right here it's O of 1, so it's O of 1, I guess, times that n. Yeah? So O of 1 work at each iteration times n iterations equals O of n work total. Okay? So that's option 0. Option 1, oh man, is there a doubly nested for loop? Well, let's break this down. So how fast is this inner for loop? Well, it's essentially the same thing, right? So it's going to be O of n inner for loop. And oh man, does this outer for loop run that inner for loop n times? And so what does that mean? It's n times an O of n algorithm, which becomes, essentially you can just pretend that this is an n. This becomes O of n squared. And this is really nice because, I mean, we could start counting all the steps all over the place, but that would just get ugly, and we know what's going to happen. Eventually we're going to drop everything and find n here, and then multiply that by n, and that's going to be our biggest thing, okay? Our dominant factor is going to be that n squared. This is an n squared algorithm. So the best case for this one is the user input was option 0. It honestly didn't really matter what n was. I guess we could go further. We could say option 0 and let's talk about that first of all. So it's option 0 is the best case, option 1 is the worst case. We could also go further. The best case is with option 0 and n equal to 0. So if we got to choose, that's the best case of all. In the worst case, if n was the same, this is assuming we can't choose n, like assuming n is the same. I should say that up here. Assuming we can't control n. We always want to go with option 0. Okay? Technically, we could make both of these constant when n happened to be 0, but let's pretend we don't have control over n. Okay, so I hope you see that there's a clear best case and there's a clear worst case in general. All right, and then finally, that brings us to two very, very famous algorithms that will be the basis of quite a few things. We're always going to be comparing ourselves in the future for all the abstract data types that we use. Like, how does this compare to linear search when we search through this abstract data type? How does this compare to binary search? Things like that. So if you haven't seen these before, I'm just going to go over them. I'm pretty sure, yeah, I'm pretty confident. I'm almost certain that these are in your book. They have to be. And yeah, I'll just go through them quickly. So linear search means you are looking for something. You are looking for a value. Okay? I don't know, like you're a hitman for ints or something, and you have been given a bounty. You must find this int. And you have no control over the input array/vector. Okay? Let's pretend it's a vector, I guess. No control over the vector. Which means that the value that you're looking for example, maybe we're looking for 1, we have no control over where that appears. Okay? So we don't know where it's going to be. And so because of that, what we'll do is we'll just search through every single index. So we have to search through every index. So we gotta start at 0, we gotta start at 1, then go to 1 if we haven't found it, then go to 2 if we haven't found it. On and on and on. And eventually, if we get past the end and we still haven't found it, we'll like return -1 or something. So we want to return the index of where we found this thing. So eventually we're going to get to 1, 2, 3, 4, 5, 6, 7, I guess. We'll return 7 if we're really looking for 1. Like, so linear search is supposed to return the index, and that's what I'm going to ask you to do in your lab. Okay, that's the idea. Okay, how fast is this? What's the worst case? And we're usually concerned about the worst case in this class. Maybe I should say that. Dun dun dun. If we're going to pick one, we're going to pick the worst case. Because if we can bring that down, that means we can have a very nice algorithm. No matter what. Even if our worst enemy picked the inputs. Okay. Back here. So that is linear search. I assume you know how to do it. Just go through each index until you find it, or you get past the end. Now, that's the question. So how long does this take? What is the running time complexity in the worst case of linear search? That's a long string of words. Worst case runtime complexity. That's what we're trying to do here. That's what we're looking for. So let's figure out. So we're going to have to use a loop, obviously. We're going to have to go through n things in the worst case. In the worst case, it's not here. And we had to search through every single place, okay? Okay, so we had to make like n total iterations of a loop body. Okay? Okay, so notice that the worst case isn't if it was at the very end, because then you'd return early. If it's not in the array at all, you still have to increment your index in the for loop. You gotta do that I++, and then the for loop's done and you can return -1. So you do have to do extra work if it's not there at all. Okay? That's the worst case. Okay? We looked through the entire array and it wasn't there. So this is we're going to execute the body of the loop n times, for n being the size of the array, and we're going to compare against each element. Okay, so if we go back to our little slide up here, executing a loop body n times, that's just n times whatever the body is, and if we're comparing, that actually just takes one step. So deep down in your processor, it's just subtracting and checking for 0. Dun dun dun. Here's where we were. So this is going to be n times constant work. Okay, so that gives us an O of n worst case. Now think about the best case. Maybe pause the video. If you got to pick your array, you got to pick the number you're looking for, which one would you pick to make your program run the fastest? I think you'd pick 8 here. Okay? Because that's the first thing there. You're going to go through your loop, one iteration, and you're going to test if it's there. Yes, it was. And you're going to return it. You're going to return index 0. So you only had to look at the first index, and it was there. So that's super nice. That's just you're setting up an iteration variable, like you're setting int I equals 0. That's super easy to do. That's O of 1. And then you're also, like, if you're checking is array of I equal to value I'm searching for, and that'll be true, and then you're going to immediately return I. So you're just doing all of these you're essentially executing 3 lines of code. Okay, so it's 3 lines of code, essentially. And those each take 1 step. So that's 3 steps. What is that in big O notation? Not O of 3, O of 1, we say. It's as if you had said 3 times 1, and we're dropping those constants in front. All right? So it's O of 1, constant time. In the best case. Normally, you're not going to have either the worst case or the best case. You're going to have some concept of the average case. So maybe we should talk about that a little bit. In the average case, it's as if this thing that you were searching for was in the middle. Yeah? I was like, all right, we're searching for the 3. It's not the best case, it's not the worst case, it's in the middle. So what does that mean? You're going through n over 2 things, all right? On the order of n over 2 things, which is dropping the constants. It's like 1/2 n. It's still O of n in the average case. Okay, so average case. You'll see that on Wikipedia. All right, so binary search. This is the fun one. If you've never seen this before, I am excited to teach it to you. So, binary search, you are ensured that you have a sorted vector, okay? You are guaranteed that. That's what it means to have binary search. Which is a pretty sweet deal, because that affects how fast you can search through it. So, did you ever play the guess the number game with somebody? Like, I'm thinking of a number between 1 and 100. Guess it as fast as possible. What is the optimal guess strategy? The first guess you should always make in that case, if it's equally likely for any number, you pick 50. And if it was too low, for example, then you'll pick 75. You're always going to have the search space, okay? Once you have, I guess, the search space to win the game optimally, right? So this is like guess the number. Okay, so you want to have that search space, and that's the optimal strategy. And that's the same strategy that you need to use for binary search. So let me pretend that we're looking for the number, I don't know, 12 in this vector, okay? Dun dun dun. I don't know the best way that I want to do this, so maybe I could make a new slide. So example, searching for 12, maybe. We'll bring this, I guess this too. So if I want 12, like the thing I'm searching for, so val, let's call it val, is 12. I'm looking for val, okay? And I'm going to start in the very middle, so 0, 1, 2, 3, 4, 5, 6, 7, 8. Here's the algorithm. We're going to find the midpoint between index 8 and index 0, so we're going to average the two. 8 plus 0 divided by 2 is 4, so we're going to start looking in the very middle, okay? So start looking in the middle. And we'll see if what we're searching for is equal to the value. We'll see if what we're searching for is equal to the value that's at that middle index. And it just so happens that it's not. Okay, so this is not the right thing that we're looking for, but we know because this is sorted, we know that it's guaranteed to not be in any of these other indices over here. Okay, that's the key step if you've never seen binary search before or you forgot about it from the textbook. Okay, the key step is at each iteration of this loop that's checking things, you can cut off half of the array or more. Technically, it's slightly more than half right now because we can skip the 38 as well. We know that if 12 is in here, it's going to be between 0 and 3, those indices. Okay, so we just cut our array in half. And now we're going to search between indices 0 and 3. So it's like 0 is our low value, 3 is our high value, and again we'll search in the middle of this smaller little array. And this is a recursive problem. And you can definitely implement this recursively, and I think your book shows that. So now we're going to pick the midpoint between 0 and 3. 0 plus 3 divided by 2, well, it's 1.5, but integer division, we're going to try 1. That's like our midpoint. Okay? So, oh man, was it there? So it took us 2 steps to find 12. Technically, it would have also taken 2 steps if it was in the same style and we did linear search, but I hope you see how fast we can get anywhere. It's because this is like symmetric, we could have found 84 just as fast. Okay? That is binary search. You're always cutting in half. Let's pretend we were searching for, you know, it's great. Let's pretend we were searching for 4 then. I'm just gonna, on the fly, change this. Let's pretend we wanted 4. So the next value that we searched for, we saw 12, and then we knew, inside of this array, that the value that we were looking for cannot be anywhere up here. Okay? It can't be in any of these. It's too big over there. So now we have changed our search space but to be between index 0, that's a W, 0 and 0. Where's the midpoint of that? Well, it's index 0. And oh man, are we going to find it in 3 iterations of the loop. Okay? And imagine that this was 88 again on the other side. It would have been just as fast. Okay? So you're always having your search space. And so let's talk about that when we talk about the runtime. Let's see here. Let's pretend we were searching for 3 one last time. Maybe I'll copy this one. Searching for 4. It's essentially the same. Let's pretend we were searching for 3 instead. So we're searching between 0 and 0, and we found that it's 4 between 0 and 0. So obviously, we need to search in the left half of our subarray. So we need to change the index that is at the top. Okay? So we need to search between, obviously, we must now search between 0 and index -1. This is like the high point, this is like the low point. And now that they've crossed each other, we'll call these like low, call this high, not lie, sorry. This is high. Okay? Now this is again new low, new high. This is now low, this is now high. Something like that is how your book is probably going to explain it. And the second that these cross, high, less than low, question mark, exclamation point, not found. Okay? The second we try to make our search space something that doesn't exist, a range of indices that makes no sense, then we're done searching. So you probably didn't even need this much explanation of binary search, but just to give you an intuition is why I did it. And now let's talk about the running time complexity of it. So, back to our array. Let me copy this. This bad boy has 8 indices from 0 to 8. Okay? And so our search space is size 9. I have 9 potential places that I could search through. Okay? The second I make my first comparison against the midpoint, okay, the array that I'm searching through shrinks in half. Okay, actually more than half. So if we were looking for 4 again, we'd start with 38, and then notice that we can search through just 0 through 3 because everything is smaller on that side. Everything's bigger over here, so there's no use looking. Okay? So we're going to have the search space every time. And eventually we're going to have it so much, like now we're searching between, like if we're searching for 4, maybe we're searching between these two. Then we're searching between these two, or this one and itself. And if we don't find it, we try and search between 2 non-existent indices. But what I'm trying to say is you can only shrink indices, you can only shrink an array that has whole things inside of it so many times. That's the key of binary search. If it never clicked for you, I hope that this line right here, read it a million times. That's what made it click for me. You can only shrink an array by half so many times and still have elements inside. Because binary search is just making a brand new pretend smaller array with half the things. Okay? It's usually more than half, but we're just going to model it as half. So the search space is initially 9, then it becomes like 4, then it becomes 2, then it becomes 1, and then if you try and divide by 2 again, you have nothing in there. Okay, so at most 5 halvings. And that is a horrible spelling of that, and I need to move this over if I want to even draw that. So at most, I could have had 5 halvings. That's a weird, fun word to say. And let's see if we can figure this out. Don't mind me. Yeah. Dun dun dun. That's not bad. So, it's essentially the floor of log of n base 2 plus 1. That's what that is. But I'm not going to write that because it's probably wrong. And this is all I want you to see, is that this is dependent on log of n. Okay? O of log base 2 of n. Halvings. And that corresponds to loop body iterations, which corresponds itself to steps of execution. You're doing constant work inside of each loop body when you're doing binary search. You can only have your array at most on the order of log base 2 of n times. The 2 is from dividing in half, and log is like how many times you needed to do that. Like how many times 2 to the what is your initial value. Okay, so that's essentially the question. It's the opposite of exponentially. So the search space that you're looking through decreases in size exponentially fast. Exponentially. Well, I guess I'll spell it out. Why not? And so the running time complexity of binary search is big O of log base 2 of n. And I hope that this informal argument makes sense. Okay, so let's see where we're going with this. Let me get through a few of these, and then we'll break for next lecture. All right, so complexity, but with more math this time, because this is a mathematical concept, big O of something. Why are we calling it O? What in the world's going on here? Why are we allowed to make these assumptions that we're making? It's all very informal. Let's fix that. Okay, so let's talk about upper and lower bounds first. So an upper bound, it's a function that's always above another. Okay, after a certain point. Okay, and same for lower bound. So lower bound for a function is something that's always below another. So here, after the coordinates 1, 1, y equals x squared is always above y equals x. So x squared is an upper bound for x. Okay? Squared is an upper bound for x. And then here, it looks like always at least wherever log base 2 of x is defined, y of x is an upper bound for log base 2 of x, and log base 2 of x is a lower bound for y equals x. Let's do it that way. It's a lower bound. And these are all vice versa, of course, for x. Okay, so if you, this is why this linear search, binary search, which one do you want to run? Exactly. Okay, so that's upper and lower bounds, and that's going to inform our definitions of big O and other things. Okay, there's a lot of math on this slide and the next few. Don't worry about it too much. Don't fret too much. I'm going to explain it very slowly, and you don't really have to memorize any of this. Everything that I showed you up here, like these hard and fast rules for big O, that's essentially all you have to remember in this class. Okay? But this is why big O makes sense mathematically. So we say that a function f, okay, where this could be f of n here, this could be another f of n, maybe we'll call this a g of n. So a function f is O of g if there are constants c and k such that f of n is less than or equal to c times g of n for all n greater than some k. So in English, what that is saying is g is an upper bound. Okay? It's saying that f grows no faster than g. Okay? So you might see this sometimes written as f equals O of g. You read that as f is O of g. F is on the order of g. Okay? It should really be written like this, but you'll have to take CSCI 26 to understand why. That's like a set. Big O creates a set of functions, if those words make sense, if you've taken that already. So g of n, n squared here, is an upper bound for 2n plus 20, because at a certain point, k, let's say, I don't know, let's choose 6, that's always bigger, but I don't know, 5.75, 5.8. If we just make k 6 at least, we're golden. Let's pretend k is 6. After that, for all n greater than k, so all the n's over here, n squared is always bigger than 2n plus 20. Okay? So after a certain point, it's always above. That's what it means to be an upper bound. That's what it means to be big O. You are bounded above. All right? And the c is useful because perhaps this was, perhaps g of n was 0.5 times n squared. I claim that this is still a true thing. G of n is still an upper bound, but you have to zoom out more. Okay, just like the rabbits. Okay, so there's a constant that you can find, and the constant is going to make the k value change. Usually, it's going to make your starting point change. Like maybe you have to go over here now until maybe you have to start at this value until this is now bigger than this one. Okay, but just think of it as upper bound. Big O means upper bound. So technically, all the things that we've been saying, while they're true, big O is a bit of a looser term, very loose. Because not only is not only is 4n plus 3, well sure, that's O of n, we've discovered that. It's also O of n squared, O of 2 to the n, because these are all upper bounds. Okay, and now we can actually discover why 4n plus 3 is O of n according to this definition. It's because I can choose a constant to put out in front of n. I can say, let's make our constant c be equal to 5, and so that makes it not n anymore, but 5n. And then eventually, 4n plus 3 is going to get overshadowed by 5n for a certain n greater than some value k. Let's choose, I don't know, 100, because then this will be 500, and then this will be 403. That can be our starting point. So that proves, a short proof, that 4n plus 3 is O of n. And you can do the same thing, though, because of upper bounds for n squared for 2 to the n. But normally, when we're talking about things, we want to pick the tightest upper bound. We like the tightest upper bound. And that means the smallest possible one. So we would like to say O of n here for 4n plus 3. We should always be saying that. And in an interview, that's exactly what will be expected of you. You don't say 2 to the n because it's usually always that. Okay? It's always upper bounded by that. That's pretty horrible. So that's some math for you. And I think that's plenty of stuff for today. I'll stop us here, and then we'll come back with some Greek terms next time. Big omega and big theta.